Good afternoon, everyone. Welcome to week 10 of structural analysis 1. This live session going on. So in the last couple of sessions, we were discussing about virtual work method. In last session, I guess we studied about virtual principle for rigid bodies and as well as for deformable bodies. So continuing on the same topic, we will be today discussing about deflection of trusses by virtual work method. Actually, it will be a step-by-step process. First, we will see the deflection of the trusses, then we will move on to the beams, and then to the frame systems. For all the three types of structural elements, we will be deducing the formulation for calculating the deflection, and then we will solve the numerical problems in each of the respective subsections. Starting with this deflection of truss by virtual work method. Here I have shown a truss member here. It's actually a three member truss. One, two, three, actually four member truss. Okay, A B C D. Okay, A B C D, and it's pinned at A and C supports. Okay, we have to find its deflection delta that it will grow under that it will undergo through forces P1 and P2. Actually, P1 and P2 are the real system of forces which are acting at joint D, and we have to determine the deflection delta here. This all thing happens in a real system. Okay, so how we will apply the virtual work method so that we can get this deflection delta. From the last class, you remember that virtual work principle for the deformable bodies that states that virtual internal work is equal to virtual external work. I told you last class virtual internal work is equal to virtual external work. We will be implementing the same principle to deduce a formulation for the computation of this deflection delta. Okay. So in trust members, the primary thing or the thing of the interest is deflection only. But in beams and frame systems, there is one more additional thing, that is the slope at any point. So for all these things, we will see how we calculate deflection. So this in this real system, we already know that under any system of loading, deflection delta in single member is given by FL by AE. Okay, so where F is the member force in that member. Okay, F is member force, and this delta is elongation in any truss member. This is in our real system, and if F is the member force developed in that member under given loading, let it be P1 and P2 acting at joint D. So for example, if you assume that the deflected shape of this truss is shown by these dotted lines. Okay, these dotted lines, the deflected shape. And because of this deflected shape, the total vertical deflection at joint B is delta. We have our job is to compute this delta because loading P1 and P2. So what we will do this, so this actually, this deflection happens in a real system. Okay. Real system. For the same truss configuration, we will draw a virtual system or a fictitious system like this. Virtual system. Okay. So in this virtual system, what things will be the constant? The configuration of the truss will be constant. Okay. Configuration of system constant. Its Boundary conditions will be constant. By constant, I mean to say that while we are transforming our real system to a virtual system, these things are not going to change. Well, support conditions or boundary conditions, they will remain the same, and the number of members and how they are joined to each other will also remain same. What will change is that we have to remove loading. Okay, remove the loading, that's real loading. Loading. These are the things we have to do, preliminary things that we need to do. Configuration will remain same, bond declaration will remain same, but we have to remove the loading that is present in our real system. Okay, this is the thing. What we will do after this is, uh, at our point of interest, we will take this figure. We have to take this figure again from here, virtual system. As I already told, our point of interest is joint B. Okay, so at joint B, we will apply a fictitious unit load in the direction in which we are assuming that it will deflect under real loads. Okay, apply unit load at point where deflection is desired, where deflection is to be computed, in fact. Okay, so we applied the fictitious unit load in the direction, in the downward direction, because we are assuming that our under given set of loading conditions, our truss member at joint B will deflect in downward directions. So I will tell you beforehand that if the deflection after computing the deflection, if the deflection comes out to be positive, positive, then our assumed direction is correct. If it comes to be negative, then we have to reverse our assumed direction. It is simple, like we assume it in the previous cases, like this integration method, conjugate P method, deflection and slopes. It's the same thing here. This thing we have to do. So we applied the fictitious load of 1 kilonewton at point B. Okay, at point B. So what we will allow is that we will allow our real system of forces, real system. I mean to say that real system, whatever deflection happen in real system, to go through the these virtual system of forces. So what will be the work done? So what we are doing is that allowing virtual system of forces to perform work while going through real displacements. So our real displacement is, I already told you, this is the real system. Displacement is delta and it is external. So what will be the external work done? In fact, external virtual work done, because this work is done by virtual system of forces. Therefore, external virtual work. Okay. I will denote it by W virtual and it's external. Okay, so W virtual external is, there is only one virtual only one load, external load in the virtual system, that is 1 kilonewton. Okay, and it is going through the real displacement delta, so total work done will be 1 into delta. Okay, so this is our equation. We will call this as equation 1. Okay, now moving, we found the external virtual work. Now we have to find what will be the internal virtual work. So, for example, let's assume that this FV is the member force developed in a virtual system. Okay. So external virtual work. Now we have to find internal virtual work. Internal virtual work. Okay. So for internal virtual work, assume or let FV be the member forces developed in our virtual system. And again, what we will do here is we will allow the virtual internal system of forces to perform work while going through real displacements. Okay. Allowing virtual internal forces to go through real internal displacements. Only then we will call it a virtual internal work displacements. Okay. So I already noted it that what will be the this is actually delta is the real internal displacements. Real internal displacements in, for example, member J. We took member J under consideration, one member. So its real deflection will be denoted as FL by AE, where F is the real member force developed in it. I will write here is okay. F member force in real system. Okay. So once I got all the quantities, then I can write now. Therefore, internal internal virtual work. And the notation that I will be using here is virtual. I denotes internal. Okay. So W virtual internal will be equal to, it will be equal to virtual forces. Okay. Internal virtual forces, that is FV. Mm, So let me, one more thing is I have to add a summation here because we were talking about only one member J. If we have to take whole configuration into system, we have to take summation J running from number of member 1 to total number of members n. Okay. So it will be force FV internal virtual force FV times the deflection that will be caused. Deflection caused is FL by AE. Okay. L by AE. We got the two things here. Okay. Let's call this equation second. Okay. So whatever virtual work principles for deformable body states that I already noted it down. WIV is equal to WEV. So equating equation 1 and equation 2 with each other, we can get this at first page. So we can write according to virtual principle for deformable bodies. Okay. Bodies, I already wrote it as uh, virtual work external. Okay, sorry, I am using this notation. VE. VE is equal to virtual work internal. When I use 1 into delta here, 1 into delta will be equal to summation FV FL by E. So if you carefully look at this equation, you will note that on the left hand side of this equation there is only one unknown, that is delta. 1 into delta, that's actually delta. So how cleverly and smartly we computed delta at our desired point using this virtual work method. So uh, this was because of, here I will write here, and this deflection. So we had this. So actually this delta is equal to FL by AE, where the uh, displacements displacements in members under given loading in real system. Okay, in real system, that is in real system loadings for P1, P2, there will be any arbitrary loading acting on our structure. But what if sometimes this is not because of the external load, the deflections will be caused in our truss member. For example, there is a temperature change in our truss structure, or there is the fabrication error. Some of the members, while joining the trust members, some of the members are either too long, or some of the members are either too short. While joining these members with each other, they will develop a stress within them. Just because of this stress and the strains in the truss members, there will be a total deflection in our truss structure. So because of these effects, temperature change and fabrication errors, there will be the deflections caused in our truss structure. So how to compute those deflections? It's very easy by using virtual work method. You just have to replace this delta that we found in this delta was because of external forces. So if this delta was caused by temperature change, so this delta will be equal to alpha times delta T into L. Do you agree with this point? Because alpha times delta T will be the strain caused in that member, and times length of that member will be the total deflection caused in that member. So if we this will be the because of temperature change of delta T in our member. And alpha, is the coefficient of thermal expansion for that particular member. Okay. So this is the same delta we have to use here, FL by AE. So our virtual work method will, this will transform to, so let me write, I will write it in different. This is the heading actually under temperature change and fabrication errors, how we will compute the deflection because of these two effects. So we have to, then what will be our virtual internal work? Okay, W virtual internal is actually equal to, it is the summation of virtual forces FV times delta. Okay, what is the delta cause? It is the summation of all the members. So it will be summation FV, what is our delta? Delta is alpha delta T times length of that member. Okay. So we can write our virtual by our virtual principle is W virtual external is equal to W virtual internal. We can write 1 times delta is equal to summation FV alpha delta T times L. This point, you will get this point cleared once we will solve some numerical problems. Okay. So this was because of that thing. And because of fabrication error, it will be the same thing. What will be the this force developed? Okay. So we had delta here, this one. So if delta will be if there was a fabrication error, so delta will be simply you have to just put delta is equal to value of fabrication error. Okay, fabrication error. Okay. So what I mean to say is like this. For example, we had class members like this. Okay, we have one trust member like this, another trust member like this. Okay, so these are joined by this thing, and this is continued like this. So it has this having one here and one more here. So now actually this member that we have to join with it like this. We have to join this with this thing now, but it's not actually up to that joint. There is a fabrication error in it. Actually, this is my short. Let's call this deflection to be delta or this fabrication error to be delta. So because of this fabrication error, there will be stressors. When they will be joining this member, they will be pulling this member so as it will fit. They will be pulling this member like this now to this joint so as to pull and put the bolts at that point. Bolts or rivets, whatever they will be using at that moment. But because of that, they have to pull it by deflection delta so that it will fit in that place. Only then the truss structure will be completed. But since we have to drag it by or we have to elongate it by a deflection delta, there will be forces caused in this member, and this whole configuration will be under the state of stress. So because of that, there will be deflections in our members. So for example, if we have to calculate the deflection at point this point B, okay, basically, if we have to calculate A, B, C, D, if we have to calculate deflection at point D, so again we will apply 1 kilonewton load here, 1 kilonewton load here, and we will assume that our truss deflects like this under this fabrication error, and this is given by delta. Then we will equate the same thing what I have done here. 1 times delta, that's the external work, virtual work, is equal to we will draw a fictitious virtual system to it. FV, that will be the virtual member forces in that virtual system times I have to just put delta here. Okay, that's all. That will be the deflection caused by fabrication error in our truss member because of fabrication error. This is deflection due to fabrication error. This is deflection. Deflection because of temperature change. Temperature change. Okay. So these two things are clear to you. Now moving forward. So this based on the same principle, we will solve one numerical problem. So in this numerical problem, there is determine the horizontal deflection at joint C, okay, of truss shown by virtual work method. So I will just enlarge it for you. So we have a truss member here is A, B, A, B, C, okay. So there is actually a 40 kilonewton load acting at joint C in downward direction. Because of this, okay, because of this, there will be deflections caused in our truss this structure. So we have to compute that deflection. So actually, if we draw its deflected shape, qualitative deflected shape, so it will look like this. It will come down. For example, this member will go to this point, but it will come a little bit down like this, and then this member will be joining so as to maintain the compatibility at the joint. So this member will be joining it like here, okay, and this will be the same thing here. This will be its deflected shape. Okay, this is actually the deflected shape of our truss under given loading. Okay, so what they are saying that so it will be moving like this from this to this point. This will be delta x. Hope you are able to see this is will be delta x, and this will be up to this point. This will be delta y. We have to only compute delta x. That's the horizontal deflection in our truss structure. So we will follow the procedure that I told you already. We will draw a real system and then we will draw a virtual fictitious system. Apply 1 kilonewton, remove all the loading from the virtual system and apply only 1 kilonewton load in the direction in which the deflection is desired. So our deflection is desired at joint C in horizontal direction. So we will be applying 1 kilonewton in horizontal direction. Okay. So let's start this problem. So first we have to do the real system of forces. Okay. Real system. So our real system is like this. The same truss member with the given loading. Okay. This thing. Okay. We have like this. So we have here and oh, so it will be given 40 kilonewton like here. This 40 kilonewton. So because of this 40 kilonewton, we will, this is A, B, C, okay. Now, so we have to, we will use method of joints to compute this. I mean to say this in member forces. First of all, we will see how the reactions will be coming. For example, so looking at the loading conditions, the reactions will be coming like this. So it's a very easy trust problem. You have solved a lot of trust problems. This reaction forces will be coming like this real system F forces. Okay. So because of this, we will try to deduce this. I mean to say that member forces in each structure. So for example, first I will show you one small calculation, then you will do all the other calculations. For example, this is AY here, this is BY here. So if we take the summation of the moments at B to be equal 0, okay, then we will write actually how much is this distance? Okay, I will write that this is actually 4, this, and this is 12, and this is 5. This is 12, this is 12 meter. You don't go on these units. Actually, these are in feet. This will be in meter. I will change it. Okay, or we can keep it in feet. Just keep it in feet. Nothing. Okay, this is in feet. Okay, and this, and keep this 40 kilo pound also. Okay, then what is the other things? This is up to this point actually. Up to this point, this is 5. This is 5 feet again here. This is 5 feet. Okay, 5 feet, 5 feet here. So we have to calculate AY and BY. So for example, we will write. So this is causing summation MB is equal 0, and we will take anti-clockwise moments as positive. Okay. So AY is causing an anti-clockwise moment of AY times 4. Okay. This is positive. Okay. So BY times no lever arm, it will be 0. And this is causing a 40 is causing a clockwise moment plus, not plus, it's causing clockwise moment, so it will be negative 40 times, and its lever arm is this. Okay, 5 feet. It's 5 feet. Okay, 40 times 5, 40. This is 40 acting this direction, and this is the 5 distance here. Okay, so actually it is causing a moment of clockwise, in clockwise direction. It's causing moment here. So it will be 40 times 5 is equal 0. Then we will get directly AY as 50 kilonewton, 50 kilopounds. Okay, AY. If you apply AY plus BY is equal to 40, vertical equilibrium, that is summation of FY is equal to 0. You will actually write AY, BY is downwards, BY is equal to 0. You can clearly get BY is equal to BY is equal to 90 kilopound. Okay. So we got AY and BY. Now you know by the method of joints, you got all the forces at AY and BY, and by method of joints, you will reduce all the forces, member forces inside. Okay. So let me take tensile forces inside, internal tensile forces as positive and compressive forces as negative. Okay. So I will be writing the forces in our this real system, internal member force in our real system. Actually, this is coming out to be 37.5. Okay. No, sorry, this is coming out to be 62.5. This is coming out to be 62.5, like this. Uh, okay. And this is tensile force. Okay. This is coming out to be 97.5. This is compressive. Okay. 97.5. And then another force in the member AB is coming out to be 37.5. 37.5. And this again is compressive. So you will be telling how you are deciding this is compressive or this is by doing the method of joints you will get these values. So let me show one small thing there. So for example, if I take this member force 97.5 here, and I have shown a direction like this. Okay, 97.5 here. Okay, let me make it like this. I have a member force inside this and this. If I cut it at this point, okay, this was showing this at this member, this was showing like this, no, like this. So it's actually pulling the member. So this is the tensile force there. Sorry, this is a compressive force there. Okay, here I will show you once again. So this member force is towards the joints. Okay, so if we draw this member, if we draw this member, so in our member, so it was like this, and the member is attached to the joint. So if we take any cross section of the member like this, if we take this cross section and we see, so what will be the internal forces developed in this so that these forces will be balanced? It is like that. This is our member. So the forces will be like this. Okay. So internally it is being compressed. Okay. Same thing is there. That's 97.5. So it will be actually minus 97.5. Okay. You are getting my point. If I have taken this 62.5 member. Okay. So if I had taken this thing 62.5. Okay, let me draw that member as well. So this is joint attached to the joints. Okay, so it is having a force of this like this attached with the joints. So I am telling that 62.5 is a tensile force. I will show you how it's tensile force. If I draw a section like here, and if I take a member there, what will be the internal forces to balance this? So to balance this arrow, and force should be acting like this. To balance this arrow, force should be acting like this. So actually it is elongating the member. So you should be seeing it's pulling the member like this direction. It's pulling the member like this direction. So it is actually tension. Okay. So it will be plus 62.5. So hope this sign convention is clear to you, because I will not be repeating it in each and every problem. You have to remember this. So this our real system of forces, we computed it. So very quickly we will draw our virtual system of forces. Okay. So virtual system of forces is again the same truss member. We have again the same truss member. We have again same truss. Okay. So this is our same truss, but what we have to do is in virtual system of forces, we have to remove the external loading. So here there will be no external loading, and we have to compute the deflection in horizontal direction. We will apply 1 kilopound load in this direction. Okay. Other things are already known, that this is 4 feet, this is 5 feet and 12 feet. I will not write it again. So quickly computing the reactions, this reaction will be 3 kilopound here, and this reaction will be 3 kilopound here, using the moment and force equilibrium equation. So please you do these things carefully once you will follow these numericals. Okay, this is virtual system. Virtual system. So quickly I am writing the internal forces because of this 1 kilopound load. This is A, B, and C. So again the forces will come here. This is this like this. This is really 3.75 in virtual system. This will be 1.25, 1.25, and this will be 1.25. This will be 3.25. Okay. This is because using the method of joints. Okay. So I will make a table for this. So I will have table like this. Okay. So in first column, I will write member. So how many members I have? So I will also write the length of member in inch. Okay. So it's given there, length of member in each. And what is the real, I mean to say that force member force developed in them in the real system, that is denoted by F, that you already know. What is the virtual member force developed in them, that is denoted by FV, you already know that. Okay. And we have to compute this product, FV times FL. I will tell you why we have to compute this product, because it's in the formula we have to use it. So its units are kilo pound square times inch. So units are important. Okay. So what are the members? We have to write member. We have member AB. Okay. We have member AC. We have member BC. Okay. These are what are the lengths in each of all these members. You can easily compute from this. We have given this 12 feet, this 5 feet, this 4 feet. We can easily compute what are the in length in inches, because this is 4 feet. So it will be 4 feet times now 1 feet is equal to 12 inch. So it will be 12 inches divided by feet. Okay. So it will be 48 inch. Okay, that's clear to you. So AB will be 48. Similarly, writing for other members as well, this will be 180 and this will be 156. Okay. So we will write force and real system. So in AB system, in AB member, we have 37.5 compressive force. I already told you how it is the compressive force. Okay. So compression is negative minus 37.5. Similarly, writing for other members, AC, I will write positive 62.5 because it's actually pulling the member. It's tensile force. So 1997.5 is in member BC. For the virtual system, writing the same thing, 1.25 minus 1.25 in AB because it's compressive, 3.75 in AC because it's tensile, and minus 3.25 in this BC because it's compressive. So when we compute this FV times FL, we have to multiply. This is column 1, this is column 2, this is column 3, this is column 4. So actually, you know what is column 5? Column 5 is equal to 2 times 3 times 4. Okay, you note that. So we will get the values like 2250 for this. We will get 4218.7 value for this, and we will get 49 comma 432.5 values for this. Okay, so what we have to take, we have to take the summation of this value. Okay, so we have to take summation FV times FL, and it will come out to be, when we sum this will be 93,870 quantity. So its unit will be kilo pound square inch. Now what our formula says is that our formula says that so I will just move. Okay, I'm writing here to make it separate like this. This is like here. This is 3 kilopound here, and this 3 I will erase. So what our formula says is that our deflection will be given as 1 times delta. We have to find it at C, and it is given as summation F V times FL by AE. Okay, so since I have to, AE is constant for each member. Okay, so we will just take AE outside the summation. It will be 1 by AE times summation FV into FL. I already told you why we were computing this summation FV times FL. Okay, so this is the summation FV times FL using this summation in this equation that I have written above, and putting the value of AE also. I can get AE I have mentioned here. Okay, please note that AE is mentioned here. Okay, so what value I will get is that first I have to write 93,870 value, and it is kilo pound square times inch. And what is the value of A and E? A is this E is actually 10,000. This is kilopound per inch square. This is the units of pressure. Times 6 inch square is the area of each member. Okay. So what I will get from this is 6 inch square is the, so this is actually 1 kilopound from this delta C. Okay. So if you will see, everything is consistent so far. If we consider the units, inch square will cancel, this kilo and square will cancel, this kilopound will cancel, then delta C will come out to be in inches only, and it comes out to be 1.56 inch. So since it is positive, so our assumed direction is correct. Delta C comes out to be 1.56 inches in right direction. Hope this method was clear to you. This is the final computation of our deflection at point C. Okay. So there is one more problem. Here I have shown it. You try it at yourself. In the same manner, you draw the real system of forces, then virtual system of forces by removing all the external loads, and you have to find the deflection at joint B. So at joint B, you will apply first horizontal load det- to determine the horizontal deflection, and you will apply a vertical unit load to apply the to get the vertical deflection. This is similar problem. And here there is a temperature drop of 15 degrees in the member A, B, and BC. So this member and this member has a temperature drop of 15 degrees, and alpha for both of them is 6.5 10 to the power minus 6 per degree Fahrenheit. So in terms of F, in terms of delta, so you have to use this. You have to use this formula now. Okay. Hope these problems you will try at yourself. Okay. Then we will move on to another topic. So actually, this is the deflection of the beams by virtual work method. So in the beams, we are concerned about two main quantities. One is the deflection at a point and slope at that point. So for example, this is my beam system shown by this beam, which is simply supported at side A and D, okay, like this. And it is subjected to an arbitrary loading, uniformly distributed load of W, and this point load P, okay, at that point. So what happens is that, for example, at a point B, we are desiring that we want to find that deflection. So let it be denoted by delta. So how we can implement the virtual work method to get this deflection delta, as well as, for example, if somebody tells that at point C, please give me the value of slope as well. Okay, theta. So the total span of this beam is L, and we have taken the infinitesimal element dx at a distance x from side A. So how we can deduce it? So let's deduce the formulation for this thing. Same thing, in order to determine the deflection at point B, as I already told in the trusses, we have to consider a virtual system or the fictitious system, in which we apply fictitious 1 kN load in a vertical direction at point B. So we will consider a virtual system for this. So virtual system will be, so virtual system. So this is our beam. Okay, the same beam, simply supported at points A and D. Okay. So it's point A, this point D, this this is point D, and we are required to find the deflection delta. So for that deflection, we have to apply a 1 kN load, 1 kN load at point B. One more thing, we are considering a small element. small element dx at a distance x from this end, okay, AB end. So actually what is this? This is a virtual system, virtual system for determining delta at B, okay, determining delta at B. So then we have to do because of this 1 kilonewton load, there will be internal bending moment, internal virtual bending moment MV developed. And on the element dx, it will perform a virtual internal work as it goes through real rotation d theta. Okay, for example, if we take this dx element in the virtual system, it will be bending like this. So there will be like this, and then we have one thing like this, and we have another. So it's our the same element, same dx element. Okay, so if I actually it was our, this is actually a exaggerated view of that initial dx element. Okay, okay, this is our element. It will have a deformation like this. Remember this is a beam element, so you remember from the simple bending theory how the deformation look like. Okay, that's why I'm making it like this thing. So initially its length was, it's not coming correct. Okay, so whatever is there, so initially its length was dx. Okay, this is the thing here. So it will be having a total rotation of d theta. So for example, uh, initially I will take it like this, and it will have internal virtual moments developed like this. Okay, that's why it's causing the bending in this element dx. Okay, mv, mv. Okay, mv, what we call mv as internal virtual moment. So for internal virtual moment, mv developed like this, and the total deflection, it will have a total slope change of d theta or rotation of d theta. So for example, we take a like this point. Okay, and I will draw one more line up to this point. Okay, so since this is the construction, that's why we have to dot them. These are not the solid lines. This is also deflected shape. Okay, So it will have a total rotation of d theta. Okay, d theta here. Okay, so from this we can have, so since virtual moment mv is acting, so what will be the small this virtual work done, dw virtual, and this is internal because of the internal virtual moment. Dwi is mv moment, mv is rotating a member through d theta. Okay, so actually mv is the internal moment, virtual moment, rotating it to a real slope, real rotation of d theta, mv d theta. Also, if we see from the pure bending theory that we have d theta, okay, slope is given as this slope, d theta is given as, we know that d theta is given as m by ei dx. Okay, okay, you remember it from simple bending theory. Okay, so d theta, we will use same d theta. So our dw, this dwi will be equal to, wait a second. So this dwvi small virtual internal work will be given as mv times, so m by ei times dx. And please note that dx m is the bending moment developed in real system. Okay, real system. So this point is clear to you. We got dwi. So if we have to compute this internal virtual work through the whole length of this beam, so total internal virtual work. Total internal virtual work will be given as W virtual internal. We have to integrate it throughout the span of this beam 0 to L as mv times m by ei dx. Okay. Also, what is the virtual external work? Virtual external work is, you already know that virtual external is, we have applied a fictitious load of 1 kilonewton times it is going through a real deflection delta. So work done will be 1 times delta. So following the principle from the virtual work for beam deflections, we have 1 times delta is equal to integral of 0 to L mv virtual moment times m moment in the real system divided by ei flexural rigidity of the beam times dx. So once again we have clever this uh, found the deflection delta using this method. So this is only the case for deflection. So for this was virtual system for determining deflection. So already wrote it's for deflection. So if we needed to find the slope at point C, so what we have to do, we have a same beam like this. Okay, what we will do, so this is A, this is D, and at point C we want to know the what is the slope at that point. So actually just like this. This will be its neutral axis. Okay, this will be its neutral axis. So at point C, we have to find the slope, and its whole length is L. The same beam with length L. So what we will do is we will apply a unit moment at that point. So at point C, we will apply a unit moment in the direction. We are assuming that the slope will be occurring in our beam. So unit moment of 1 kilonewton meter. Okay. We will take same element, small element dx at a distance x, and we will use the same formulation that we obtained from above. So what will be the deflection cause? So here the only virtual external work will be changed to the expression virtual. So one thing I forgot is this is virtual system for determining slope theta. Okay. So what will be the virtual external work? Virtual external work will be, so there is a moment of 1 kilonewton meter. This is 1 kilonewton meter, and it is going through a real rotation theta. Okay, real rotation theta. Okay, this is the real rotation theta at point C. It's going a real rotation theta at point C. So 1 times theta. So using the virtual work principle, we will get 1 times theta is equal to same internal virtual work will be the same, mv virtual moment times real moment m divided by flux rigidity ei times dx. So smartly we were able to compute the slope at point C. So this is slope. Okay, this is for deflection. So this was again a very easy formulation for computing deflection using virtual work method. Okay, so quickly this thing. So quickly we have a problem here, one small problem here. So what is saying in this? Determine the slope and deflection at point A. This is actually a fixed cantilever beam fixed at B and free and A. So at free and A, uh, free and we have to determine the deflection delta A and slope theta A. Okay, so how we will be dealing with this problem is that first we have to draw the real system. Okay, it is subjected to a triangular rod like this. Okay, ei is constant flexural rigidity, so real system will be, so our beam will be like this. Our beam is like this, it is fixed from this point. So what are the forces that are acting on it? So there's a triangular load like this, triangular load like this. So this is side A, this is side B. So let us consider a segment at a distance x from this. Okay, so whole length is L, the span of the beam L, and this ordinate is W as it is shown in this figure. So using the similar triangles, we will get this ordinate to be equal to Wx by L. Okay, this is clear to you. Wx by L. This is the real system for moment M. Okay, then For virtual system, first we will draw virtual system. Virtual system for determining the slope. Okay, virtual system for determining theta A. It will be the same beam like this. Sorry, it will be the same beam like this. You have to do only one thing: remove the loading, free end A, free end B, and apply a unit moment at that point. Okay, so this is one. And this one is in the direction we are assuming the slope will be happening. So this is x again. Okay, so the span is again L. So we will draw another virtual system for determining the deflection theta A. So the beam will again remain same. So in virtual system, external loading is removed. Only apply 1 kilonewton load at the point where the deflection is desired. Okay, 1 kilonewton. So this is A, this is B. Again, the span is L. I'm not going to write it. So to calculate the moment calculation, virtual moment at a distance x, we'll consider a section at a distance x here. Okay. So let's write the moment in this. First in this, we will write the moment, real moment, M. For 0 less than x less than L, what will be the real moment? M will be equal to, so this, okay. Let us take this clockwise moments as positive, okay. At a section x, what will be the moment? It will be area under this triangle. One minus time is 1/2 of what is base x, what is altitude w x by L, okay. So what is our moment coming out to be real moment? Minus 1 by 2 wx square by L, okay. This is M. Sorry, I didn't multiply it by the lever arm. So lever arm will be like some, it will be at a distance of x by 3, okay. Multiplied by x by 3. So it will be x by 3 here, okay. So what will be the virtual moment for determining the deflection, determining the slope mv. So mv will be actually equal to, so we have taken clockwise moment as positive. So at a section x, mvx, it will be 1, okay, since it is in clockwise direction. This one is in clockwise direction. So in this, for determining the deflection delta, taking the clockwise moments as positive, mv will be equal to, for 0 less than x less than L, mv will be equal to, mv will be equal to minus 1 times x. That's equal to minus x, okay, because this is causing a anti-clockwise moment here, okay. So we will use our formulations like for deflection, for slope and deflection, okay. So for slope, at a, so what will be the slope at a? It will be 1 times theta a. It will be equal to 1 times theta a, integral of 0 to L m v times m divided by a e, not a e e I, e I times dx. Substitute all the values. So it will be theta a only, 0 to L. What is mv? Mv is 1, okay. Mv is 1. So real moment is wx cube by 6L, okay. And it's minus wx cube by 6L, and ei is multiplied, okay. There, ei. So when you will solve this integral, you will get theta a to be equal to minus wl cube divided by 24 ei. Okay, so since this is coming out to be negative, so our assumed deflection direction, so this direction is wrong. Actual direction is this. Okay, so we have to take this as this one. Theta A will be direction opposite of the unit moment. Okay, so this will be WL cube divided by 24 EI, and our direction will be like this. Okay, so at this point, at this point I have shown this should be like this, no? This. For slope at A, for deflection at A, we will use the same formulation. 1 times delta of A will be equal to 0 to L mvm dx by EI. So quickly putting the value delta A will be equal to 0 to L. mv is minus x. I already computed it. Okay, here minus x. So m is minus wx cube by 6ei. 6l actually, ei is multiplied in the formula dx. When you will compute this value, delta a comes out to be wl power 4 divided by 30 ei. Okay, 30 ei. So since it's positive, so our assumed direction of the load is actually the direction of the deflection as well. So assume a direction of the load. So load will be downward, but deflection will be also downward. So it's obvious from the figure loading that deflection will be downward. WL power 4 by 30 EI. Okay, and it will be downwards. Okay, so you see how we calculated this slope at point A, deflection at point A using these formulas. Thank you everyone for joining. This was all for today. Okay, so one more thing, I have given some more problems here. Please you practice them at home. Example of problems, okay? So this is homework for you. Okay, thank you.